Welcome to Module 2 Build Effective Generative AI Solutions in Your Organization. Prompt engineering isn't just a technical exercise, it's a shared responsibility. Business users need prompt literacy to get accurate, useful outputs from AI tools in everyday workflows. Developers and AI specialists use advanced prompt engineering techniques to optimize models and build reliable solutions. What is a prompt? A prompt is the input text or instruction that guides a generative AI model to produce an output. Think of it as the starting point for a conversation with the AI. Why prompt matter? Well-crafted prompts improve efficiency by reducing the need for multiple revisions, deliver outputs that align with business goals, reduce risk by minimizing misinterpretation. Prompt engineering is essential for maximizing generative AI's effectiveness. Business users should craft clear goal-oriented prompts with context, source data, and formatting expectations to guide AI responses. Developers go deeper, using structured templates, few-shot learning, and dynamic prompt generation to ensure scalable, reliable outputs. Leaders must understand both approaches to support responsible AI use across teams. Business prompts focus on clarity and relevance for everyday tasks, while developer prompts optimize performance in applications. Together, these techniques empower organizations to harness AI responsibly and efficiently across functions like marketing, support, and engineering. The machine learning lifecycle is a structured, iterative process involving five key stages: defining the task, preparing data, training and validating models, deploying models, and monitoring performance through MLOps. Business leaders play a vital role in shaping goals, ensuring data readiness, and evaluating outcomes. Continuous monitoring and refinement are essential, as models must evolve with changing data and business needs. This lifecycle ensures that machine learning initiatives remain aligned with strategic objectives and deliver measurable value. Before adopting machine learning, organizations should assess four key areas: data readiness, ensuring clean, sufficient, and representative data; technical expertise, securing skilled data scientists or ML engineers; infrastructure, having adequate compute resources for training and deployment; and return on investment, evaluating whether expected business impact justifies costs. Addressing these factors helps avoid missteps and ensures ML initiatives align with strategic goals and technical capabilities. Organizations deciding whether to build custom machine learning, ML, solutions or use pre-built services must weigh strategic, technical, and operational factors. Custom solutions are ideal when business requirements are highly specialized, proprietary data offers a competitive edge, or complex compliance and security needs exist. These efforts demand strong internal expertise and justify investment when differentiation is critical. In contrast, pre-built services such as Azure AI are better suited for standard predictive tasks, especially when technical resources are limited, time to value is a priority, or upfront investment needs to be minimized. Leaders should ask, do we have the data, skills, and infrastructure to build in-house? Will the benefits outweigh the cost compared to using existing services? What's our timeline for realizing value? Not every organization needs to build from scratch. Leveraging pre-built tools can accelerate deployment and reduce risk. Ultimately, ML complements generative AI by enabling prediction, personalization, and automation. Strategic decisions should align with business goals, technical capabilities, and ROI expectations. Understanding the ML lifecycle and readiness factors helps leaders choose the right path, whether building for long-term advantage or buying for speed and efficiency. Machine learning, ML, models operate by learning patterns from data to make predictions. At their core, ML models are mathematical functions that map input features X to output predictions Y. The process begins with training, where the model is exposed to historical data containing both features and known outcomes, labels Y. These features might include variables like temperature, age, or flipper length, depending on the use case. The model uses algorithms to identify relationships between inputs and outputs, resulting in a function y odd fx that can generalize to new data. Once trained, the model enters the inferencing phase, where it applies the learned function to new input data to generate predictions. For example, given temperature and rainfall, the model might predict ice cream sales, or using medical data like weight and glucose levels, it could estimate diabetes risk. In wildlife studies, features like flipper length and bill width help classify penguin species. This life cycle, training followed by inferencing, is foundational to ML applications. Training requires labeled datasets and computational resources, while inferencing enables real time decision making. The model's effectiveness depends on the quality of data, the relevance of features, and the appropriateness of the algorithm used. Understanding this process is crucial for business and technical leaders alike. It demystifies how ML models work and highlights the importance of data preparation, algorithm selection, and continuous evaluation. Whether predicting sales, diagnosing health risks, or automating classification tasks, ML models transform raw data into actionable insights through a structured learning process. Machine learning models fall into two main categories: supervised and unsupervised learning, each suited to different prediction tasks. Supervised learning uses labeled data, where both input features and known outcomes are provided, to train models that predict future outcomes. It includes regression for predicting numeric values, e.g., sales prices, fuel efficiency; binary classification for two category outcomes, e.g., diabetes risk, loan default; multi-class classification for multiple categories, e.g., penguin species, movie genres. Unsupervised learning uses data with only input features and no labels. The most common technique is clustering, which groups similar observations, e.g., customer segments, flower types. Clustering helps uncover natural patterns and can even inform future supervised models by defining categories. Understanding these types helps leaders choose the right ML approach for their business goals and ensures technical teams apply the most effective methods. Deep learning uses artificial neural networks inspired by biological neurons to solve complex problems. In these networks, each neuron is a mathematical function that processes inputs, x, and weights, w, through an activation function. When stacked in multiple layers, they form deep neural networks, DNNs, capable of handling tasks like regression, classification, natural language processing, and computer vision. The training process involves four steps: forward pass, inputs flow through the network to produce predictions, y; loss calculation, the model compares predictions to actual outcomes, y, to measure error; weight adjustment, it updates weights to reduce error and improve accuracy; iteration, this cycle repeats until the model achieves acceptable performance. The final model contains optimized weights that enable accurate predictions. Though computationally intensive, this iterative learning allows deep learning models to automate tasks once considered too complex. This example illustrates how a deep neural network classifies penguin species using physical measurements such as bill length, bill depth, flipper length, and body weight. These features are fed into the input layer, where each value activates a corresponding neuron. The data then flows through hidden layers, where neurons compute weighted sums and apply activation functions to detect patterns. These intermediate results pass through the network via forward connections, culminating in the output layer, which uses a softmax function to produce a probability distribution across three species: Adelie, Gentoo, and Chinstrap. In this case, the model outputs probabilities of 0.2 for Adelie, 0.7 for Gentoo, and 0.1 for Chinstrap, predicting Gentoo as the most likely species. This process demonstrates how deep learning models make decisions by combining simple mathematical operations across many layers. The model learns from training data to recognize complex relationships that humans might not explicitly define, enabling it to generalize and make accurate predictions on new inputs. Such models are powerful tools for automating classification tasks and can be adapted to various domains, from medical diagnostics to customer segmentation. Their strength lies in learning intricate patterns and delivering high accuracy results through iterative training. Neural networks learn by adjusting internal weights to improve prediction accuracy through an iterative process. Training begins with data preparation, where input features and known labels are fed into the network. During forward propagation, neurons apply initial weights to compute outputs. These predictions, y, are compared to actual values, y using a loss function which measures error. The model then performs weight optimization using gradient descent, calculating how each weight affects the loss. Through backpropagation, these adjustments are applied across all layers. This cycle repeats over multiple epochs until the model minimizes error and achieves reliable accuracy. To build successful AI solutions, organizations must focus on four key pillars: prompt engineering and retrieval augmented generation, RAG. Crafting effective prompts and grounding AI outputs in verified data ensures accuracy and trust. Data quality and security, reliable representative data, and strong security practices are essential for responsible AI, reducing risk and supporting compliance. Machine learning lifecycle. Understanding when and how machine learning adds value beyond generative AI helps guide business decisions and resource planning. Build versus buy decisions. Evaluating whether to develop custom solutions or use pre built services helps maximize ROI, minimize risk, and accelerate time to value. Together, these elements support informed decision making, ethical implementation, and sustained innovation. Next, video chapter 2: Drive business value with AI solutions.